So, hi, good evening. Welcome to that week 9. It's a open session or summary session. So, about the week 9. So, almost we are end of the most of the algorithms. There is a 10th week of strings pattern, that pattern matching of strings, but that is not included in your end term examination. But the 11th week is there, that is exclusively, some advanced concepts of data structures and algorithms. Algorithms, we have advanced concepts of algorithms. But there mostly we don't find any kind of specific algorithms. But mostly whatever the algorithms we learn is almost ended in by the 9th week only. 10th week is a optional week. And the 11th week concept which you are learning is exclusively advanced algo concepts. So that is what. So I think I'll share my screen. Please acknowledge that whether my screen.
Sir,
Yeah, yeah.
in the textbook, no, week 11 content is not there. So,
Week
is it
9
there?
or week 10? Just a
Week
minute.
11.
Just yeah, it is correct, correct. So actually there is, see, is my screen visible?
Yeah.
Yes,
This,
sir.
yeah, actually this has to be shown like string algorithms has to be week 10 and this has to be 11. But anyway, this is the optional one. Week 12 string magic pattern algorithms are optional. It's not there. This is extra content only. It's a provided, but there is no quiz or end-term examination on this up to this one. So this, of course, this linear programming and network flows is not there. In this, no complex algorithms, only conceptual things are there. So up to 9 is a different algorithms, right? So even OPP examination, which you are facing in, I think, 17th of August, I think so. That will be up to week 9 only. Okay. So I think it's clear, right? Yeah. Okay. Shall I proceed for the content then? Great. So let I think actually this is that the GitHub only. Why? Because week 9 there are a lot of things to be discussed, like different problems of this particular dynamic programming. So I just summarized it that whatever the GitHub notes is there, the same thing converted into PDF. So let me quickly walk through that. So what really this dynamic programming is. So this could be the very important thing, concept of it, and algorithms what you are learning or problems you are solving. They are standard problems. What you are really doing is standard problems. So now let's see that generally whenever we do that a recursive kind of approach or any kind of problem, general kind of approaches. So divide a problem into sub problems. That generally we do it. So that is generally we do that. So dividing a problem into the sub problems. But whenever we do that, the sub problems are there. These sub problem solutions, these sub problem solutions, we combine to achieve. So main problem, whatever the sub problems, each individual solution we are getting, that we are combining together and we are getting the major problems. But there is a issue. That issue is called overlapping. Overlapping is nothing but repeating. Repeating task we do it. Whatever you did it, again you might have to repeat it. So this is the disadvantage of that. Whenever you do that, a problem you are dividing into sub problems, and we try to solve the sub problems, and by solving the sub problems, we achieve that main problem. So that what happens if there is a overlapping issues there. So when the overlapping issue is there, that computation takes time. The computation takes time. A lot of CPU time you are using it. So that to avoid it, we are using this DP approach, dynamic programming approach. This is what is the core idea of this dynamic programming, why the dynamic programming is. Is it clear? Why really the dynamic programming is? Yeah. So I think it's clear what I trying to share that initially what's the need of this dynamic programming is. Yeah. So now let's move to that. This is the dynamic programming about it. If you could see that a solution to the original program can be divided or derived from combining the subproblem solutions. Example, the factorial, insertion sort, Fibonacci series. What you can say that if it is a factorial we are talking about, if you want that factorial of 5, we try to do that factorial of 4. So when you want factorial of 4, you try to do that factorial of 1. So keep doing this until we reach that the factorial of 0. So whenever the factorial of 0 is reached, we try to return that value 1. This particular factorial of 3 is returned to the factorial of 4. So the factorial of 4 is returned to the factorial of 5. So this is what is happening. So these are some example problems where you can solve it through dynamic programming. But one thing is that anticipate the structure of the program. You know, whatever the problem you're trying to solve it, you need to identify that what are its subproblems. To solve the main problem, what subproblems you need to solve it. In that, where it is overlapping is that overlapping we try to avoid it. So the next important thing is here, you should make inductive structure, the basic kind of inductive structure or mathematical formula. So you need to derive it based on the implementation and based on that subproblems we are making. We try to build the inductive structure. Whatever standard problems you are doing right now, every standard problem has an inductive structure. So one thing is that solve the subproblems in the topological order. You know, the subproblems we are solving is that always in topological order. That is one direction only. Like you can say that top to bottom or bottom to top, something like that. So that is what really the dynamic programming is what it's talking about. Now, so whenever we talk about the dynamic programming, as I said, it is overlapping issues there whenever recursive problems you are solving. So let's see something more about it. You see that. So generally, the memoization we use it. The memoization is very simple, pretty simple. We are generating the solutions. The solutions we want to put it inside the memory. So inside the memory, we want to put the particular subproblem solutions. For example, this is solution 0, solution 1, solution 2, solution 3, solution 4, solution 5. So this particular solution, if it is already generated, something you got it. This solution already we got it. For example, while we are solving the particular subproblem 2, you might require that already available solution you want to use it, you can use it so that this can be solved. Whenever the solution 3 you are calculating, you might require the help of that solution 2. So you can use it. So that we preserve earlier solutions. If earlier solution is already available, we'll pick out from that. If it is not available, we compute it. If that solution is already available, we pick it from that memo and then we are using it. If it is not available, we recompute it. So for this, simply what we use it as per Python implementation, we use dictionaries simply, because whatever that upcoming problem you are looking, there we are using it as recursive solution along with memoization. Now let's see that. So here is that. So are you able to see the simple recursive solution? Hello, are you able to see
Sure.
that? Great. So can anybody say that what is the complexity of this particular Fibonacci of n? Sorry, recursive Fibonacci of n?
2 power n.
Yes, correct. So maybe you can expand it. If you could say that Fibonacci of 5, so you have a calling of that Fibonacci of 4, Fibonacci of 3. So similar lines, if you go over it, it goes to here, something like this, it goes to here, something like this. So at this level, maybe the number of calls are this at this level, the number of calls is this. When it goes to this level, it's going to be the 2 square. So keep doing. Definitely the complexity it goes to that 2 power n, because repeated things we are calling, that is happening. So the Fibonacci, nth Fibonacci you wanted using recursion, what I want to tell you is, so some tasks we are repeatedly we are calling, because already Fibonacci of 3 is there, the Fibonacci of 4 it has to call, the Fibonacci of 3 it has to call, and Fibonacci of 2 it has to call. So that they want to tell you. Here you can look at. See, this is a diagrammatical representation. So you can have a look. These particular operations are overlapped operations. See, these Fibonacci of 2, Fibonacci of 2, Fibonacci 2, or you called it is again repeated times of 3 times. Because already it is, once it is computed, why 2 more times I need to call? Similar lines. This Fibonacci of 1, we are calling 3 times. 1 time calling is enough. So this is called, overlapping issue. Overlapping. So whatever that task is already done, again we are recomputing, already it is available. To avoid it, the basic implementation is this. It is a recursive one, but we preserve that earlier solution so that we can use it. So you can have a look. This is a memo. The memo is empty dictionary. As I said, the memo is maintained like a dictionary. So whenever this n value is less than or equal to 1, simply we put that. So memo of n is at 0. Sorry, 0th Fibonacci is 0. First Fibonacci is 1. See, look at here. Because every particular value available here is definitely, this is the key. You can say that. This is the key. What I want to tell you is this is the key, because dictionary contains this. This is the value. So whenever less than or equal to 1, we got it. Simply the 0th Fibonacci is 0. First Fibonacci is 1. Because this is the simple base case. And whenever you come to here, whenever n is not in that memo, for example, I'm trying to call that Fibonacci of 3. So definitely n is not available because there is no value for this particular key. Of course, key also not there. Then what I do is Fibonacci of n minus 1 and n minus 2 you are calling. To compute this n, we try to call this n minus 1, we try to call this n minus 2. Again, this one is being computed, n minus 1 is computed because recursively you are calling, no. This n minus 1 is computed. So by using this and this, these values, what happens is already available. So we try to compute this one with the combination of these two plus we got 1. So similar lines, this nth one is computed with these two so that we got it is 2. Once it is available, I need not recompute it. For example, this 4th Fibonacci I wanted, so it is calling 3rd Fibonacci. 3rd Fibonacci is already available. I can get it from this particular memo. I need not call recursion again. Just I can get it from memo. And 2nd Fibonacci is already available. So I can get it from here. These two I can do it. I got that 4th Fibonacci. That's what we do that. We'll put it in this particular one. If it is available, just return it. If it is not available, we'll recompute it. So that you will have that, avoiding that repeated task. So if you could expand it, this particular tree without overlapping, it looks like this. See, whatever I said, like, dictionary key and value, they said it is like a k and this. So Fibonacci of 3, once it is called, again, whenever it's calling, I can reuse the solution. Whatever solution we got it, I can reuse from the dictionary. Again, I need not do that. Fibonacci of 2, once it is available, again, I need not do it, just I can use it. So in this case, what happens, the complexity is very much reduced. So how much you reduced, can anybody say that? Can anybody say that? Maybe, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if this is n value, n is nothing but 5, n is nothing but fifth Fibonacci I wanted, the complexity is just greater than or equal to O of n. Is it right? Is it right?
Yes, sir.
So that using memoization, we can avoid that the exponential complexity. So that is what advantage of using the memoization. See, memoization also a DP technique. Somebody they thought that does memoization is a DP? Yes, memoization also a DP technique. This memoization is also a DP technique. Sorry, memoization. Sorry, yeah, this is memoization. In the DP, we have a other approach, which is called another approach, which is called tabulation. This is also DP, but this is called tabulation. Very simple. The memoization will use top-down approach. Top-down approach. So whatever the recursion we use it, the same thing we use it, but past computed recursive results we want to preserve it. This particular one is bottom-up. See what exactly bottom-up approach means. So in this particular top-down approach, the main problem divided into sub-problems, and after solving the sub-problems, we use that sub-problem solution. But here what happens, first we'll fix the base case. From the base case to main problem, we travel towards top. That is called tabulation. So simply, in all of the case, I can say that the smart recursion is called DP. What do you say? Is it right? Is it right? Is it right or wrong? Hello.
Sir, what's that?
Smart recursion. General conventional naive approach recursion, if you write it, the complexity goes to the 2 to the power of n, right?
Smart recursion is?
Best one. We can say that optimized recursion, right? You are reducing the complexity, no? Is it right? Is it right?
Yes, sir.
A naive approach of recursion takes 2 to the power of n, right? Right?
Yes.
So if you are applying that memoization, just we are getting complexity more than just O of n. It's not at all that 2 to the power of n. But still one more thing is there, dynamic programming. See, the dynamic programming, what simply they are doing is, it's a bottom-up approach. So I don't want to talk about this right now, because I'll get back to that. What code is this? This pictorial representation is very interesting. See, what I'll do is, this particular values initially I'll fix to the subproblems. Fibonacci of 0 is a subproblem. So this is 0. This is the Fibonacci of 1 is a subproblem. This is 1. Is it right? Is it right? Is it right?
Yes, sir.
So to calculate the Fibonacci of 2, what should I do is, sum of this Fibonacci of 0 and Fibonacci of 1, if I do it, I can get this one. Is it right?
Yes.
Similar way, the Fibonacci of 3 I want it means I can do that. Sum of this Fibonacci of 2 and Fibonacci of 1 I can do it, so that I can get this one. So similar lines, if I want Fibonacci of 4, I supposed to do that. Sum of this Fibonacci of 3 and Fibonacci of 2, I can get this one. So still we are going to the top. Fibonacci of 5, we can derive it using that. Sum of the Fibonacci of 4 and Fibonacci of 3, I can get this. So this is called bottom-up approach.
Sir, in the previous approach, we were doing the same thing, no? But just we were coming from the top and then
Correct. But still you can optimize. So not just it is O of n greater than, we want to bring it to O of n. So see, look at here. This implementation is interesting. You can see this one. So do you see this here? What it is doing is, it is filling this particular list. T is a list. it is filling with all of them zeros, right? Because as per it's a list, right?
Yes, sir.
For example, you are taking n value is 5, the list is created with 6 elements because n plus 1 they didn't know, right? Right?
Okay,
Hello.
sir.
So
Yes, sir.
all these are filled with 0 first. So let us assume that this particular one is filling with 1. So because after that initialization pass we have done, this one done, this one done. So this one is changed to 1 after this particular instruction line number 3. Then what I'm doing is from 2 to this part I am traversing. In this part what I'm doing is current I want to calculate with previous I minus 1 and I minus 2, right? Right?
Yes, sir.
So that I can compute this one is 1. Similar way, this is 2. These two, if you do it, addition of it, we get 3. These two, we get it, it's a 5. So we can say that nth Fibonacci, if you want it that, fifth Fibonacci, we are getting is that 5. So this is exactly very good complexity is improved efficiently. It is often simply we are filling a table. What you call this kind of approach is called as tabulation. Filling the table from bottom up approach. Let us assume it is a single dimension one because we are not entered into that two-dimensional problems. Right now it's a single dimension. So you are filling it as bottom up. So simply we are identifying the base cases. Using base cases we are trying to see here the base cases are identified, that is 0 and 1. Using 0 and 1 we are moving to the top. So 0, 1 solution is used for 2. 1 and 2 solution is used for 3. 2 and 3 solution is used for 4, something like that. So this is a impressive and interesting kind of solution where you can say that mostly we implement dynamic programming means the tabulation approach only. So somebody is interested to do the memoization, they can implement it. But exactly we get the complexities that often only not more than that. Is it clear?
Sir, but the thing is, both are giving the same similar complexities.
No. Just it is greater than, no. Just it is. You can check it. See that? Oh, sorry. This is why it is going. Just a minute. Uh, yeah. This is why it is scrolling. I don't know. Yeah. See, look at here. This is, yeah, this is actually just manually calculated. If n is 5, how many times you are calling is maybe if you can consider this is first time, second time, third time, fourth time, fifth time, 6 and 7, 8 and 9, right? Right? Of course,
Yes, sir.
sorry. Yeah, it is right because there is no overlapping is there. 9 is there, just greater than or equal to O of n, right? Not exactly O of n. That's what. Still, we want to improve it means we go for tabulation approach only. Even whatever problems further we are solving, also we are solving through tabulation. Okay.
Sir, but once we have calculated this lower values, values for, I mean, let's say fib 5, then we wanted to get the values of fib 4 and fib 3. Once we calculate fib 3, then we are just reusing that. Na?
Reusing.
Sir, so in that case, why is the
Just a minute.
complexity?
I will some particular issues there. Just I'll reopen my things because it is not erasing something. It not looks good. Delete this. Maybe I try to use it single color only. Maybe that it might be no problem. Yeah. So let's move to this part. Okay, is it right?
Yes, sir.
Okay. Yeah, tell me. So,
Sir, to calculate fib5, I want fib4 and fib3. Now, to calculate fib4, I want fib3 and fib2. To calculate fib3, and so on. So, ultimately, I'll calculate
oh,
fib1 and fib0, and
so
I'll memoize it.
correct, correct. So maybe this is not required, right?
Yes, sir.
This red color is not required. Let's
Yes.
consider that. Yeah, in this case, it is just greater than maybe 5 elements means maybe it's going for 6, right? That's it. Yeah. Okay, maybe you're right. Memoization also. Okay. Yeah.
Okay, sir.
Yeah. So most of the solutions we are solving in further is always tabulation. Shall I proceed for the next one? Is it okay? I think everyone got the
Yes.
concept. Others, please.
Yes, sir.
Yes,
Any
sir.
clarification? Yeah. Great. So this dynamic programming approach, whenever we want to solve it, the most important thing is identifying the base case. So then only we can build that bottom-up solution. So sub-problem solution we are reusing to solve the main problem. That is called, a ladder kind of walking, so where you are moving from bottom up. So let's go for that. There is some standard problems are given. These standard problems will give you that overall idea how this dynamic programming is working. So let's see that this is one standard problem. Grid paths. So if you can consider this grid path, this is what the grid path is. So there is a rectangular grid. Always the grid we are moving is one way of roads. This is what problem statement. And this one way of moving, okay, that's clear. Yeah, one way of moving, there are only two directions of moving. So that is one step top. This is, go up, and one step right. So this way I can go. So you can move from left to right, you can move from bottom to top. Only these two directions are allowed. So this problem is we are trying to identify. So let's assume that this is a source. This is a source. And this is a destination. From source to destination, we are trying to identify what are the different unique ways to reach from source to destination. That we are trying to identify. So to do this problem, the interesting thing it happens, see that whenever you solve this kind of what we are trying to do is, so we try to fill that first the base case, because I'm not going directly to the inductive structure. Let me walk through that. Whatever the base case is there, from the base case, how do you do that? For example, let us consider these are the points we are trying to reach. Is it right? These are the points, no, we are trying to reach. Always one step right and one step top. Is it right? Is it right or wrong?
Yes.
Yes, sir.
So what I do is from this particular 0, location to this, I required that one step forward. From this particular location to this location, one step forward I need to go. From this to here, there is a one step. From this to here, there is a one step. From this to here, there is a one step. So that to reach from this 0 to the last, you have only one path. Like, going towards is this. Right? Right? Now, similar lines, going from 0 to this is 1. So this is 1. This is 1. Similar way. I'm sorry, maybe, we are trying to reach from this one to, I'm sorry, maybe that's okay pretty much, but okay, I'm going for bottom up is right. That's okay. Yeah, not a problem. Yeah. Maybe all filling, I may not do that. Okay, this is clear. So in this way, if you do that, so 0 to this particular 0, to this location, we can say that this is 0, 1. This is 0, 2. Maybe I'm writing index position inside. This is 0, 3. This is 0, 4. This is 0, 5. Yeah, it's clear. Yeah. So these are what the points we are trying to move. In this way, if you go for it, So this is going to be that keep on moving. So definitely it's going to be that 10 and 0. Is it right? Is it right?
Yes.
Hello. So these
Yes.
points, if we are moving, we are going into 10 and 0. Now the thing is, the interesting thing, actually, I did not go for further. Whenever we are moving, there is a blockage points also they'll give it. We'll forget about the blockage points. So we'll do that later. If this is a simple kind of grid, so let's assume that these are the points, these are the points. So I'm taking a simple example. This is 0, 0. This is 0, 1. This is 1, 1. This is 1, 0. This is clear. Now the thing is, to reach from this 0, 0 to 1, 1, how many different ways are there? It's pretty clear. So I can go in this way, because as per the directions they said, one step right and one step up. And similar way, another way is there. This way also I can go. Is it right? Is it right?
Yes, sir.
So how do you compute this one? This number of ways to reach from 0, 0 to 1, 1 is number of ways to reach is the 2. Is it right? Is it right?
Yes,
Yes,
sir.
sir.
So how would you compute this one? How would you compute this one is simply addition of these two. Am I right? Am I right? Is it right? Hello.
Yes,
Sir,
sir.
how did you get this, sir?
That's what. First I'm filling the base cases, right? These are the
Yes.
base cases, I filled it. So I
Yes.
filled this, all these are ones, all these are ones, right? Right?
Yes, sir.
To compute this particular grid point, how many ways you required is, I need to do this particular top left corner one, bottom right corner one. I can do the addition, right?
Okay, sir.
So now we go further. Now we are investigating. See how many grid paths are available to reach from 0, 0 to mn. Mn is nothing but m number of rows and n number of columns. Let's assume that. So here, of course, these are all the conditions what they say that. So we can move that each path is, move up is nothing but the j minus 1. So move right is nothing but I minus 1. So in this way we are moving. If you're doing this one, to reach from this 0, 0 to this 510, there are 1358 ways are there. So whatever you have seen this particular ways, like blue color line is there, there is a yellow colored one, there is a red color is there. Similar kind of way, if you try to reach it, there you can find another way also. Is it right? Is it right?
Yes.
So in that unique different paths, if you find out it, to reach from this 0, 0 to 510, that is target, there are 1358 different paths are there. So now if you understand how this particular 2 is calculated as sum of this particular top left corner and bottom right corner. For example, I want to say that to calculate this I and j, let's assume this is I, this is I, this is j. Is it right? Let's assume this one.
Sir,
Hmm.
so this 1358 paths is including the paths through these holes or no?
Including the
Paths through these holes.
through this
Holes, holes.
hole. What's the hole?
This non-available point
No, no,
0.
that we'll discuss, please wait. That we'll discuss. But right now, we are targeting how this 2 is calculated, right?
Uh,
How this 2 is calculated is this ij, how you are calculating is, we are trying to calculate that I minus 1. If this is I, this is I minus 1. Is it right?
yes.
Right?
Hmm. Yes.
If this is j, this is j minus 1, right?
Yes.
So these two addition we are doing. so that this particular 2 is calculated. How this 3 is calculated is using the sum of these two. How this 4 is calculated is sum of these two. So similar lines we are going, but whenever there is a blockage area is there, we try to have the blockage area is no reachability. So the blockage areas we are filling with zeros initially. So what way these base cases are filled? This is base cases. This is a base case. So whenever you are filling the base case, you supposed to fill the blockage areas also. These are called, blocks. We are not allowed to enter into it. So whenever you are not allowed to enter into it, this reachability is 0. So if you do the sum of these two, you get the 6. Is it right?
Okay.
So similar with this 26 and 0, we get it is 26. So here the inductive structure is given. See here you can see that there is inductive structure is defined. I think, wait, I'll find it somewhere. Yeah, maybe it was there somewhere else. Yeah, maybe it was missed. But anyway, I'll give you that what is the inductive structure of this one is very simple. So the matrix, sorry, I'm going to the top. Yeah. The current matrix, let's you consider this is a DP matrix. It's a 2-dimensional DP matrix. The current I and J is computed with combination of M previous I minus J plus previous I and J minus 1.
J minus
Is it right?
Yes.
This is a inductive structure. This entire one is that inductive structure. So this you need to trace out it. After you identified the base cases, how the current value or current problem is computed is using the previous two subproblems. So the previous two problems are that previous I, that is I minus 1, the previous J index position, these two things if you sum it, so we'll get a top left corner value plus bottom right corner value. We can compute that current cell value. So wherever blockage is there, of course, we are putting initially 0 itself. So this is the conceptually how you are doing. So conceptually, is it clear?
Yes.
If anybody have any clarification, please raise your hand, because conceptually, if it's clear, just quickly we understand what is the code they have written at. Any clarification, please let me know. Yeah, great. So this is the practical. See, anyway, we'll come to that Memoization, and this one is his way. But forget about this particular situation. We understand this situation is later. So now the practical implementation, you see that. Yeah, it is a recursive one. This is a DP one, which is bottom-up approach they are using. Yeah, correct. This is a bottom-up approach. Yeah, correct. See, look at here. So do you know NumPy array? It will fill all of them zeros, right? Right?
Yes, sir. NumPy 0.
Yeah. So because NumPy 0 we are creating, so the number of rows and columns what we are giving is, there is a barrier also it takes, which is a blockage section of the grid where it is not allowed. That's we have done. Now we are trying to repeat inner and outer loop where it is m and n times, or we can say that x and y times. What do you say that? So here, whenever I and j and I is equal to this 0 and j is equal to 0, the base case ones you are filling. Is it right?
Yeah.
So you are filling base case ones. All ones are filled at the 0th row of I and 0th column of j. So that all j's of this one is filled with 1, 1, 1. So all this is filled with 1, 1, 1. So rest of them, of course, it contains the zeros. We don't worry about that. Zeros, it remains also no problem. Now, so this is, you are trying to computing that current DP solution using base case. So what I do is, if barrier is available, we remind 0. Whenever barrier value, maybe the barrier value we are giving a tuple value, maybe you are saying that 5th row and 6th column is a barrier. So if this particular 5th row and 6th column, maybe something like that, right? Barrier is a tuple. Barrier is a tuple. No, is it right?
Should be list of tuples.
No, maybe you can give it list of tuples also, no problem.
Because you using in
Correct, correct.
this
Yeah, yeah, correct, correct, correct.
tuple
Maybe,
in
maybe, maybe barriers you have given is 5 and 6 is there, 7 and 9 is there, something like this. Maybe you're right. Correct. So every I and j, we try to check it whether it belongs to barrier or not. If it belongs to barrier, we remain 0. We leave that is 0. Whenever it's not a barrier, we try to compute that previous row and previous column. That is, top left corner, bottom right corner. We compute that current I and j. That's simply we have done. So finally, what you return is maybe checking of the matrix which was generated, the complete calculated one, and we try to find out that integer converted value of that. So that is, last value, maybe, this top right corner, the final value of this, I want it. This is the final indexed value of m and n. So this m and n I want it. So that final value we are getting. That is what returning this is. Yeah, it is integer value of this last. Of course, integer is not required. Maybe they are using it. So here it is a barrier points they have given it. Yeah, you're right. Whatever you said, it is barrier points at different locations they have given. So then they are trying to do that calling of grid tab, the tabulation part. They are doing this. So hope you understand this bottom-up approach, right? Okay.
So this is for finding how many paths are possible to a point, right?
Correct. From source to destination.
Okay.
So beginning of the grid to end of the grid. Okay. Yeah. Okay. Now there is a issue. See, look at here. This is what one interesting edge case. What you can say is there is a edge case. Trade-off between recursive technique and iteration. So for example, you are trying to use DP approach only. DP approach, yes, you know that. DP approach, what do you do that? So generally we try to fill this one. All this is once we are filling, right? All this is once we are filling. Is it right? Is it right?
Yes, sir.
Yes,
So
sir.
bottom up we are trying to go, no? So that we try to fill all these are. So after that, we are trying to compute all this part using this. So whatever that, this matrix we can call it is, so M matrix. So I and J is computed with, so I minus 1 and J, and this something you are calculating. This all part you are calculating, right? Right?
Yes, sir.
After you all calculated, there is a barriers here. After reaching these points, we identified the barriers are here, right? So when these are barriers, so this entire computation is no use. Is it right? Is it right?
Yes, sir.
So
Because there is no path from.
correct. So whatever the values you calculated so far, these are not at all useful. Again, you are getting here these two addition. If you do it again, 1. So these two addition is 1. 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 Similar lines. If you go this, so this is 1. This is 1 because these two you are calculating 1, 1. So 1, 1, 1, 1, and this is 1. Of course, sorry, this is a 2 because these two you are doing. So to reach from 0, 0 to this particular one, only 2 different unique paths are there. That is this path and this path. Am I right? Am I right?
Yes.
So at this time, so here the dynamic programming, it wouldn't help you because the complexity, it reaches to that all these extra computations you do that, it is reaching to that m into m. Instead of it, if you are using recursion and memoization concept, it will take just m plus n only. These kind of edge cases are there because sometimes we feel always tabulation is better than memoization, but sometimes it fails. This is one of the edge case. They want to give you that. Sometimes there is a trade-off. Trade-off means there is a balance between, iterative approach of DP tabulation and recursive approach is better than that, tabulation part. So hope you got this point, right? So why I'm telling is maybe enter what they'll do is they will give a grid. They'll give a grid. They try to make you that. So maybe they will not give it this much of bigger grid. What they want to ask you is they might give it all of the blockages here. Maybe, not the blockages. This part is a blockages one. This part is a blockages things they are given. So they try to ask you that. So of course here there are, here the blockages they will give it. So then you need not waste this computing of this part. Only this is the only one way. This is the only one way. How many different ways they might ask you that? So only two ways. So you need not compute all the stuff and wasting of the time for this question. Simply you can figure out that going the top right is one way and going the right top is a one way. Simply it is solved. So these kind of questions, actually, whenever the quiz examination, we try to represent with one particular grid and we try to give the edge cases. Of course, I found that some of the previous pattern of question paper, generally professors has make these kind of questions are somewhat tricky to identify the edge case. So I think you got this problem. Any clarification? Is it clear? Yeah, great. Cool. So now let's move to that another standard problem. This is the problem number 1 where it is a grid path. So now we go to that another standard problem. This is longest common subword. See, there is a difference between a subsequence and subword. Please try to identify because most of them will confuse there. So what they feel is subsequence is different. Subsequence can have skipping or bypassing of characters, right? Skipping or bypassing of characters. Maybe you can skip it. But subword is not like that. At a stretch, you required a single length. What do you say that, single length? So there is no bypass. It's a subword. Subword does not have bypassing. It's a single at a stretch it is. So actually, I did not directly go for this. I don't want to go for this inductive structure because whenever complex the problem is there, we are suggested to ask it in the question using a quiz question. We definitely give a note. This inductive structure we give as a guidance so that using inductive structure you can compute it. But I don't want to talk about inductive structure now. Basically, there are two strings are given. If you could see that two strings are secret and bisect is given. If you could see that the S1 string is secret and S2 string is bisect. So if you could see that the common subword, the longest common subword is, so there is SEC, there is SEC. So this part and this part is matching. So remember, we cannot skip it. Like, sect we cannot do it because somebody might feel it. Here also T matching, here also T matching. No. So subword means at a stretch, a single pool of characters. We don't have bypassing or skipping of characters. That's what called subword. Now the thing is, is there any easy way? So DP is the only way to easily solve it. So by filling the base cases, from the base cases to we reach that, top of the problem, like sub problem to main problem, we are trying to do that. For this, very simple, we try to create number of columns, that is S1 string length plus 1, and number of rows S2 string plus 1. So if you could see that, so this is what exactly they did it. So see this one here, there are secret is there, plus 1 they did it. Why this plus 1 is, let's assume this one is a none character. So everybody knows the Python concept of none. Somebody says that other language people, they call it is null. Maybe, a not useful character. Similar lines, this particular bisect is the +1. So why this +1 is, maybe they consider it is a not useful character, which is called null. So they are creating the number of rows and number of columns in terms of this, rows and columns. So now this you can consider, maybe somebody says that these are, you can say that it is columns, because as per that J, so as per this one is, you can say that it's I. Maybe, everybody prefers that I is used as row and J is used as column. Now the thing is, what is the base case? Why do you fill it? What do you fill it? So it's pretty simple. I want to tell you that a simple question. If S1 is ABC, maybe standard simple understanding, S2 is none. So what is that longest common subword? Is there any longest common subword? Is there any longest common subword between S1 and S2?
No common.
So that here LCW value is 0. Is it right?
Yes, sir.
Similar line, same reverse if you do it. Maybe S2 contains that ABC and S1 contains none. So at this time also LCW is 0. This is a kind of base case. What do you say that, the base cases we are filling. So let's do that. So what simply they are doing, you see that here. This could be the base case. This is the base case. They try to fill this one. Similar lines, this they are trying to fill it. See, I'll tell you how they are filling this. See, for example, this particular none. So we are trying to match with, does none, is it matching with yes? No. So we are filling with 0. Is it matching with E? No. We are filling with 0. Is it matching with this? No. Is it matching with this? No. Matching with this? No. No. Similar lines, this we are trying to do that. This none, is it matching with this? B? No. So that we are filling with 0. This. So we have filled it. Like, if you consider this is maybe, you're filling from this is 0, 0. Maybe you can consider. So at this moment, if you come to here, so this is 6 and 6 because additional character they have taken it. So these base cases we are filling. Once these base cases are filled, so how do you find out this one is, there are two cases are there. Matched case is there, unmatched case is there. So whenever matched, what do you do? Whenever unmatched, what do you do? So very simple, whenever matched, so let's consider not matched case. Whenever not matched case is there, we fill with 0. Simply we fill with 0. So whenever matched is there, this is the first case, there is a first condition. Whenever matched case is there, we try to calculate. So what do you calculate is, we try to do that. Let's consider this matrix is maybe LCW, we can call this dynamic programming matrix, we call this is LCW. So what I do is 1 plus, so LCW of I plus 1 and j plus 1. That's it. So let's consider, how do you get this one is, pretty simple. If this is I and j, if you are doing it is I and j, this is I and j. So I plus 1 and j plus 1. So if you could go for, maybe I said it is I is nothing but going to the next row. Is it right? Is it right? Next row, no? If this is I plus 1. Is it right? Hello?
Yes, sir.
So if this
Yes.
is j, this is j plus 1, right?
Yes, sir.
So in this way, if it is j plus 1, this column, so I plus 1 if this column, we go for it. So whenever you do this one, so definitely this value we are getting. So what you can say is bottom right corner value plus 1 you are doing. So this is a plus 1 whenever matching is done. So you can see that here T is matched with this T. Is it right? Is it matched or not?
Yes.
Yes, sir.
So
Match.
whenever match, immediately what I do is the bottom right corner value we are getting, so that I plus 1 and j plus 1. So that is the next row, next column value we are picking out. So by picking up that plus 1 you do it. So by that we are getting it whenever matching. But whenever t compared with e, there is no possibility. So whenever this particular t compare with r, there is no possibility. Whenever t compare with c, no possibility. Whenever t compare with e, no possibility. Whenever t compare with s, no possibility. That's all done. This row is done. Now we are coming to the C. The interesting thing happens. Up to the year, there is no matching, so that C cannot be matched with RET. Whenever C is matched with C, we got it is 1 because this one plus 1. This one plus 1. Now, so once this is done, no further matching at this place. But whenever you come to the E, there is a previous matching value 1 is there. This one plus 1. So that we got it 2. Similar way, S is there. Previous already matching value is there, that is 2. So that 2 plus 1 we got it is 3. So we got this value by computing the previous matched value. The most recent matched value, if anything, is that I try to use that one plus 1. If most recent matched value is 0, so no previous one, so current one plus 1 is added. If previous matched one value is already more than 0 is there, that one plus current matching one, it is definitely it is increased. So you can look at this inductive structure. What I said is, if matching is happened, the character at the position of that I and character at position of j is matched. So what I do is I try to pick the previous matched value, that is I plus 1 and j plus 1 you do it. Whenever no matching, just we fill with 0. This is how you are filling this DP matrix in the tabulation format. This is one of the standard problem of the DP. If we want to ask in the examination, generally what we ask is that there are 2 words we are giving. We try to ask you that how many number of, longest common subword is there. But of course, it could be the simple one asked, but there is a tricky question also. I'll tell you what the question is. So I think conceptually, is it clear? Any clarification?
Hello,
Yeah.
sir. If the length of words are different, then it is considered to
Lengths
be.
can be different also, no problem. Even lengths can be different also. That's what they said it is. Creating that number of rows of columns is that. So we are trying to create the table m plus 1, n plus 1. So where it is first string length of that plus 1, second string length of it also, because whenever lengths are different, the shorter string character none is there as a last. Is it right? Is
Oh,
it right?
yeah,
So
yeah.
the bigger string, it has some alphabet, right?
Yes.
So then also there is no matching. Yeah, over. Simple.
Okay.
Now you see that the implementation, see, this is a simple and easy implementation. As usual, we are taking a numpy array, importing. We are creating all zeros first. So here, the maximum words it is matching, how many number of maximum words it is matching. So actually they want to find out the maximum, maximum number of characters, how it is matching. That's what they want to find out it. So now you look at here, this decrement they are doing n minus 1 to, because always we are filling from 6th index to this, 6th index to this. because we are filling from 6th index to 5th index, 5th index to 4th index. So that's the reason the loop is in reverse order. These loops are in reverse order. So whenever loops are in reverse order, the matching is happened. The previous, of course, I said it is I plus 1 and j plus 1. They said it is r plus 1 and c plus 1. Maybe the variables are different. Whenever no matching is done, that is just we are putting with 0. Now the thing is, the maximum number of characters matched also we need to find it or no. This maximum matching is right now 0. As and when first matching is found, max W will be updated with 1. Is it right? Is it right? Hello?
Yes, sir.
Yes, sir.
If more than 1 is found, more than 1 means here we found it, this one. This is a more than 1. Whenever this more than 1 is there, this is updated with 2. Whenever more than 2 is there, that's 3. This is updated with 3. So finally, this condition is just picking out the maximum value. That's it. Like, a list of numbers are there. In that, I want to find out the maximum. So every time this is also executed. Finally, what do you return is maximum length of that is called, longest common subword length. We are trying to find out it between the bisect and secret. That is, SEC is the common longest subword. That is called LCW. So that we have traced out it. So hope you got it. Is it clear? So that's what we got it is 3. Is it clear? Conceptually and implementation also. So the complexity, it reminds that M and N. So if it's clear, I want to ask you one past quiz question, because generally I found it some interesting question in the past term, because I don't remember which term it belongs to. So is it clear? Shall I ask now question?
Yes, sir.
Yes, sir.
Okay. So they might give you this. See, so they will give you one particular string S1, secret. So second S2, they might give it red sec. Red sec. Can anybody say that? What is LCW, longest common subword matched?
SEC.
No, length of that, is it 3?
3.
3.
So anybody have a confusion, maybe somebody might feel this part and this part is matched. Okay. So this part and this part is matched. They try to say that. So the longest common subword, somebody might, this part and this part is matched, this part and this part is matched. So they try to say that, anybody wants to say that, 6, it is totally wrong. Because initial itself I said is longest common subword means at a stretch. There is no skipping and bypassing. So how many longest common subwords are there also? Here you can say it is one word only. Is it right? Is it right?
Yes, sir.
Is it right?
One word only. Yes, sir.
So shouldn't it be 2, sir?
Wait, so that's what I want to confirm. So here LCW is 3. LCW is 3. Longest common matched is 3. How many similar kind of 3 length of LCWs are there?
RET and
Two words are there. 2 words are there, which is having that LCW of 3. That is what, actually for this, you need not apply any kind of implementation. So any kind of, inductive structure to do that. A tabulation also, you not do that. Simply use it, how many, the length of the longest common subword is 3. The number of words which is matching for the 3 is the 2 words. So this is matched and this is matched with same length of 3. So that the right answer is 2. If this one is asked, it is a 2. The length of common subword is 3. So this kind of tricky question, most of the people will do a mistake. So where I found in the past kind of scorecards and as well as the pattern behavior, generally you might have been a little kind of ambiguity while you are answering it. I think it's clear, right?
Yes, sir.
Okay.
Yes, sir.
Yeah. So this is another standard problem. Now, as LCW is over, there is another interesting problem of DP, that is longest common subsequence. This is, as I said, subsequence means there is a chance of that skipping of possibility, like you can skip it. If you can see that, the same thing of S1 is secret, S1 is secret, S2 is bisect, S2 is bisect. If you could see that. So the length of that LCS, which is longest common subsequence, you have a skipping of characters. In this case, what you can say is, I can avoid this part. So I can avoid this part. If you avoid this one, you can find it SECT sect, and I can avoid this part. So that matching parts is these two. So LCS value is 4. Is it right? Is it right? Length of that LCS is 4. Is it
Yes.
right?
Yes.
So similar lines, whatever you did it for LCW, similar lines only we do. Just index to structure is little bit change of it. So what I do is, instead of doing, bottom right value, we try to take that right value and left value, whatever that, So right side one and left side one. So don't say that left side one. Right side one and bottom value. What you can say that? Right side value and bottom value. Out of these two, so whenever matching is happened, that's okay. Maybe the previous matching plus continued. Whenever not matching is there, the index to structure is somewhat different. What you can do that is, we pick the right side value, we pick that bottom value, and out of these two, maximum we are getting, the maximum. So let's see that. See, same kind of arrangement. They try to fix this one, the base cases. Initially, the base cases are here. These are the base cases. So these are the base cases. We try to fill it. N plus 1 and N plus 1. Now, the filling of this one is very simple. So whenever there is a match, simply we try to do this one plus 1 whenever matching is happening. So if you could see that there is no matching, so T, you're trying to match with E, there is no match. Whenever there is no match, maximum of this green, because you want to find out this value, so maximum of this and this. These two maximum we are finding it. So either the previous matching is available anything, or that means current S2 string matching with S1 is available, or previous one, like S1 matching is available here with S2 match, like the previous match. Either this one is available, this one is available. Out of these two, whichever that earlier matching is bigger. So in this way, if you go, interesting thing here is, so you can look at here. See here, whenever C, you are comparing with E, this particular C you are comparing with E, out of these two, the maximum we are picking. So the maximum means this two only we are picking out. So this is, how do you track it? We are trying to pick out that right side value and bottom value. So the right side value, we can say that it is J plus 1. So the bottom value, we can say that it is I plus 1. So whenever J is increasing, I is constant. So we can say that I and this, we can say that I plus 1 and J. This is what index to structure. You can have a look. So there is a matching is happened. simply the previous one, whatever we have done is same. Whenever not matching, earlier we filled with 0, we ignore the previous matchings. Just we ignore the previous matchings. But now we don't ignore it. In the previous matchings, out of these two matchings, which one is bigger? Whether till now the right side matchings are higher or bottom matchings are higher, out of these two, maximum we are picking out. That maximum we are updating. So this particular one is similar kind of problem. Even it is skipping of that particular characters also, you can identify that LCS value. So that's what a core, see, definitely if it is a complexity problem, this LCS inductive structure will give it. Without inductive structure, we don't ask it. Definitely we'll ask it. Because to make it simple, we'll ask it. To make it simple, we'll ask means simply you can draw a one grid and you can identify. If this is I at J, this is going to be that I plus 1 if it is going towards right. Sorry, J plus 1, because column wise you are going, this is going to be I plus 1. If you are going to the top value, that is different, I minus 1 and J minus 1. That is because you are going from bottom up approach. So hope you got it. So here also you can see implementation is very simple, because conceptually if you understand, implementation is pretty straightforward. Like zeros you are filling, you are going in reverse order of loops. Whenever matching is happened, the previous inductive structure only we are following. Whenever not matching is happened, we try to get that maximum of that right or maximum of the bottom. So out of these two, maximum we are updating. So finally, the result is available at top 0 column. So final top one. So this is the final result. So 0 index position, you contains the final matched subsequence value. So that is we are returning. This is. So totally the length of that LCS value is 4. So here also complexity, you supposed to traverse that entire M cross N matrix, so that the inner loop and outer loop is available. The inner loop is repeated outer loop number of times. So definitely the complexity is so O of Mn. Okay. So these two problems mostly it looks like same. So if it is clear, then we have, so third problem also almost similar, some little complex. Is it clear?
Yes, sir.
Yeah. Yes, sir. Just give me, yeah, just 2 minutes. I'll get back. Yeah, so thanks for it. So now, so edit distances. See, when one particular word you want to transfer to another word, like transformation of words, like so I'm not taking the similar kind of example, maybe too easy to understand. If you could say that this edit distance problem, so S1, you take it a string called Monday, and S2 it contains the Tuesday. So whenever you want to transform S1 string to S2 or S2 string to S1, generally the transformation, we try to do 3 operations. So what we do with the transformation operations we do is, we try to replace or update a character, or you try to delete a character, you try to add a character. These are 3 operations we do. Is it right? If you want to transform this S1 words to S2, otherwise S2 word to S1, some replacements to be done, some deletions to be done, or some additions to be done. So all these are called, distances, what you can call, each operation can be considered as a one value of distance. How many number of transformations to be done, like replacements, deletes, all these cumulative. For example, to convert this Monday to Tuesday, what's supposed to be done? Like I want to convert this Monday to Tuesday. So day and day is similar. Is it right? Is it right? Hello?
Yes, sir.
Day and day is similar. What I supposed to do for MON is, I supposed to do this MON has to be replaced with 3 characters of TUE, so that, hello, yeah. Somebody wants to ask something? Okay. Yeah. So this day and day is similar. So I can say that, oh, sorry. Wait, something, there's an issue with my pad. Yeah. This day and day is similar. We don't worry about this. This Monday we want to convert into Tuesday means this MON will be replaced with TUE. So that we can say that 3 replacements and 1 character I need to add it. So that 1 adding of character. So totally we required 4 operations. Is it right?
Yes, sir.
Similar lines, same thing happens. Day and day is same. This TUE will be replaced with MON plus 1 delete, so that 3 replacements plus 1 delete operation. So this is also 4. Of course, if you calculate the distance from S1 to S2, similar distance is there from S2 to S1 also. That is generally we do it. But here also inductive structure is exhibited, like, maybe whenever you're filling, so that edit distances you are trying to calculate. But let me come back to the edit inductive structure later. Now we see this here. There is a matching character is there, not matching character is there. So whenever matching character is there, simply take the previous value. What you can say that if this is matched, take the previous value. For example, let you see that one. Whatever you are filling here, 0, how do you get this one is, there is a matching happened. So we try to get the previous value. For example, T and T is matched. We try to grab the value from the base case. So this base case is there, no? From this base case, we try to get the value, so that we got it. This, that is called matching, whenever matching is there, because no replacements are required. Just get 0. That's it. No replacements are required. 0 means. Now, whenever not matching is there, so for example, to convert this T to ET, what I supposed to do is, minimum of these 3. So I'm just marking with blue color, minimum of these 3, like these 3, plus 1. So minimum of these 3 plus 1. So what exactly, if this is, if you consider, as I said, it is J is wrapping towards columns, I is wrapping towards rows. If you could say that, this is considered as that I and J plus 1. Is it right? Is it right? This is considered as I plus 1 and J plus 1, right?
Yes, sir.
This one. This is considered as, this is okay, yeah. This is I plus 1 and J. Is it right?
Yes,
Yes,
sir.
sir.
Out of these three, the minimum one we are picking out, the minimum one of these three plus one. So of course, this is also included. So out of these three, minimum one is 0, 0 plus 1. So what exactly the t, if you want to transform into et, you require that one substitution or one deletion, or it might be that one addition, because t and t is already matched plus 1. Similar way, when you are trying to get with RET, we are trying to get minimum of these three plus 1. So minimum of these three is 1 plus 2. Already the previous one is there plus 1. So in this way, if you go again, the result it reaches to here. So you can look at the inductor structure. See, whenever matching is happened, just you get the previous value, which is called, bottom right corner value. Whenever not matching is there, we try to pick the value. So the bottom right corner one. So this is I plus 1 is the bottom one. This is bottom right corner. This is the bottom one. What you can say is the bottom one. This is exclusively the right side one. This is bottom right corner, diagonal value, what you can say is. So out of these three, we are getting minimum plus 1. So this is inductive structure. So that if this inductive structure is mandated for whatever that LCW problem, LCS, of course, even the grid path also, they did not give that inductive structure. But implicitly, we can say that there is an inductive structure. You can calculate. So by using the base case, we are computing the current INJ, we are computing the previous INJ values. So that is what we do it. So here also the tabulation is done with m plus n plus 1 grids only you are creating the same. So you can say that here the edit distances, the same numpy as usual, nothing great we have done. So you can see that here there is, updating of the edge cases. Here interesting thing happens. We don't want to fill this one as, zeros. So this is a base case, right? This is the base case, no, right? Is it right? Hello?
Yes, sir.
Similar way, this is also base case. This part is also base case. This part is base case. That means 6, 5, 4, 3, 2, 1 is a base case. So what exactly is this particular none? When you compare with this none, no replacement. This none, whenever it wants to replace with, transform into t, one replacement is required. This none, when you want to transform into et, two replacements are required. This none, whenever you want to replace with RET, you require 3 replacement. So that's what the base cases are updated here. Interesting way. See here, m plus I is updated. Here n plus j is updated. Sorry, minus j is updated. So 1, 2, 3, 4. So that way, or you can say that. So in this way, if you are filling, this j value is 0. 6 minus 0 is 6. 6 minus 1 is 5. 6 minus 2 is 4. In that way, it is filling. Similar way, when it comes to here in reverse order, so 6 minus I value, it's a 0 is 6. 6 minus I value is 1 when it is going towards down. So we are getting, that's incremented I value, definitely decreases your base case value. So here only the base cases, they are filling in different way. But rest of the things is, internal loop and outer loop, they are as usual, m cross n times. This is matched kind of calculation. This is unmatched kind of calculation. Taking that 3 corner values, out of that minimum we are picking plus 1. 3 corners. Current value is computed, 3 corners of this one. Yeah, it is finally the topmost left corner value we are getting the edit distance. Totally 4 things to be done. In this case of, secret has to be transformed into the bisect. We required that 4 replacements. So the 4 replacements is some deletions, some additions, and some kind of additions, deletions, and as well as replacements also. Yeah, I think it's clear. Mostly this concept also it is same, because most of the dynamic programming concept what you are learning is, it is giving you practice of what are the three corners of the current value we are computing, whether you are picking up the right corner one, bottom one, or you are picking out the diagonal value. So what you are picking, so that's we have to aware about it. So that is all done. Once again, if you walk through this particular Professor Madhavan has been given a very good kind of a lengthy session. So in that session also he clearly said, if this is I and this is J, how can you get it the right side value? How can you get it the bottom value? How can you get the diagonal value? So simply he said about this I plus 1 and J plus 1, and this is I plus 1 and J plus 1. So that kind of thing, only thing, if you recap the session, maybe higher speed of forwarding of this lecture, or Madhavan's lecture, that would help you. Yeah, I think it's clear. Any clarification? Is it okay? Is this okay?
Sir, will we be given questions on reading of the result from a graph? Like, instead of
Exactly.
giving the words, they'll just give that graph and those numbers, and they'll ask us to find.
Definitely. In the past kind of previous questions, maybe I'm not pretty sure, but I can still remember some kind of question in the quiz or end term. That means end term means quiz only, of course. Yeah, here it is. Or maybe other rough work. Maybe I found it this kind of question. Maybe they'll give it. There is a particular matrix. Maybe they want to ask you a question like this grid path, but they don't give it that a larger grid. They might give you a smaller grid, something like 0 to 4 and 5. There might be that this way. Yeah, it is okay. This kind of thing. So might ask you like this. This could be that. Yeah, it is 0, 1, 2, 3, 4, and 5. They might ask you in this way. So similar lines, it is 0th one, first one, second one, third one, fourth one. Of course, they might use it another one, or it might be uniform one or not. They might ask you that what is that final location of this. Actually, even they don't give it 5 cross 5, they might ask you 4 cross 5 or 5 cross 4. So they might give you one blockage area also. They might mark it, this is a blockage area. This kind of thing, they'll fill it with dark color. This kind of thing, they want to fill it the darker color. So you need to find out that what is the different unique paths to reach from this 0, 0 to this 5, 5. So in this case, you need to fill it like 1, 1, 1, 1 quickly. They don't ask you very complex one. They might ask you that very simple one, like this is 1, 1, 1, and 1 and 1. So in this way, if you go like this is calculated with 2, right? Is it 2? This is 3. This is 4, right? This is 5, right? This is 6. Is it right? Hello.
Yes, sir.
Yes, sir.
So in this way, if you go, so maybe you compute it like these two are calculated. So whenever these two are calculated, this will become 3. These two are calculated to 6. This is 10. This is 15. This is 21. So when you come to here, it's a 4. When you come to here, there is no possibility of reaching. It's a 0, right? Is it 0? It's also 0. So when it is 0, these two are computed, it's going to be 10. These two are computed, there is no possibility, it's a 0. These two are then 21 is repeated same. Here it's a 5. Here it is 5 and 0, it's a 5 only. This is 15. This is again 15 because these two are computed. This 15 and 21, it's going to be 36. Similar lines, it's a 6. It's a 10. Sorry, it's 11. Because these two it is 16, 26. These two, it's a 15 is there, and this is 21 and 41, and this 41 is 47 and 77. This reachability is 77 unique ways. Of course, they don't ask you even this much of bigger size. I found in some particular quiz examination, This forecast one. They won't ask you that a bigger grid path. They might ask you this is one particular one, and another one, as I said, they might give you 5x5 only, but the block case they'll give you a corner cases. They'll give the corner cases the blocks. Then you might need not waste the time at this place. Just simply we can find out what is the direct way to compute. Okay. Yeah, I found it. Some questions are there. Okay.
Yes, sir. And even in this graph, in edit distance, like using these lines to find whether it was an insert or a delete or a substitute.
They will ask
So
you
I
simple words only. They don't ask you like Anil and Anu, you can find it. How many replacements? They don't ask you a bigger word and then you tell me what is that replacements in that. A smaller words and easy to identify, simple like Monday and Tuesday, Anil and Anu, such kind of thing. Okay. At that
so
case,
sir,
you need not draw that even grid path. Sorry, DP matrix you not draw it. Simply you can calculate, right?
sir, like if they don't give like the words, but just like the grid part of edit distance, and then they'll ask us in this two words what were like inserts or deletes. So
Correct. Correct.
I think it
There
was
might be a
like
chance.
some
There might be a
vertical
chance.
line was an insert and horizontal line is like a delete.
No, not like that. So vertical line is not horizontal. I don't find such way. So they might ask you a grid, sorry, edit distance is like this. They might give a particular word like this, Anil, and they might ask you a
No,
word
sir,
called.
without the word, like just the numbers of
No,
that.
no. I don't find such
Okay.
kind of thing. Yeah, I don't find it. Differently, edit distance means particularly you require two strings. What two strings are there? What replacements has to be done? How many?
Like, will they just not give the
No,
final
no,
grid
no,
without those words?
no.
Okay.
Without
Okay.
no. I don't find that kind of question is very weak question. I can say that. I can say that that doesn't give you the sense of the concept, right? Okay. Yeah. What
Sir,
concept they want to test it, that concept only they'll ask it. I don't find such kind of questions. Yeah. Sorry.
sir,
Hmm.
so in the edit distance and
Hmm.
also in LCW and other one,
Hmm.
so according to the implementation in edit distance, it is like saying I plus one and j plus one. It
Hmm.
is not exactly taking the bottom values. It is taking the upper values.
So actually you have filled it. So if you could see that, yeah, this could be, yeah, here it is. So here, so you are running the loop is in reverse order, right?
Yes, sir.
So current value of this I, we are filling with the previous values, right?
Yes, sir.
So if this is, for example, if this is I and j, clear? This
Yes.
is I and j, clear?
Yes.
So what is this index position?
This is 3, 4.
No. Of course, maybe it's 3 comma 4 or something like that. So I can say that I is constant, j plus 1, right?
Yes.
So that we got the right side value, right?
Mm-hmm.
Similar lines, this one, if you can say that. So if this is I and j, this can be like, I plus 1 is this and j is same, right?
Okay.
So whenever you come to here, this is I plus 1 and j plus 1, right?
Yes, sir.
So whenever there is no similarity, we try to take the minimum of these three. That is implemented in the code. Did you find it? This
Yes.
is,
Yes. Yeah.
okay, min function.
Okay. Got it.
Yeah, got it. Good. So yeah, mostly these problems are similar problems. Only thing is you might remember that what is my base case. If you are able to trace out that base case, you can easily figure out that whatever upper cases are. So and one more thing, mostly even the OPP examination. So if you could see that the OPP examination, if you notice that earlier PYQs of OPP examination, mostly one-dimensional DPs only they are asking. Is it right? Hello.
Yes, sir.
So because they don't want to make it too complex questions in the DP, but if they want to ask you the two-dimensional DP questions, definitely you can find in the quiz. Quiz means enter, like multiple choice. So MSQs, there they are asking. But mostly in the OPP examination, you can find sales cost prediction, like where the problems it looks like hacker rank and lead code kind of problems, like staircase. When you are stepping into the staircase, at a time 2 steps we can jump, always it is stop, something like that. So always these are one-dimensional DPs only. They never ask you the two-dimensional, because they don't want to make it complex kind of problem. But the graphs problem, they are asking for 30 marks. Because why I'm talking about this is upcoming one OPP examination. Easiest problem they are giving is linked list. And some complexity problem they are asking for something like log n complexity of binary search complexity. Graph problems they are asking for 30 marks, right? Is it right? Is it right?
Yes, sir.
Like Dijkstra's algorithm, they try to ask you DFS or something like the outside story, they are changing it. Shortest distance, they are trying to find out it. So for this, it's a 30. 20 marks is given for linked list kind of problems. So here it is come to the 50. 25 marks and 25 marks is given for other problems. Maybe one of the problem they might ask you the DP. One of the problem they might ask you that greedy approach. So
there is binary search too.
yeah, maybe log n complexity also they'll ask you that. Binary search is 25 marks. Generally, this pattern of question paper where I noticed it, the earlier things. So that don't worry about two-dimensional kind of implementation in the OPP examination, but should care about the concept during end-term examination. Yeah.
So DP is very important. Huh?
DP is very important for two cases. Two-dimensional DPs are very important. The standard problems, what we discussed, is very important for end-term examination, where MCQs and MSQs you are able to answer. One-dimensional DP approaches are useful because I think upcoming Friday session, you will have that 4 problems on DP, practical implementation. There you can find some problems of one-dimensional problems also, where you are coding, you are implementing. There are different problems, whatever we discussed so far now. Yeah, that time also so interesting one. Yeah. Is it clear? The DP is very important. Yeah.
Sir, what means the optimal solution means?
Minimum one or maximum?
Hello?
Minimum one or maximum? Optimal means either maximum you are expecting or minimum you are expecting. What is the best? So in the case of that edit distance, or you can say that number of maximum paths. So a grid path, we are expecting maximum paths to reach from source to destination, right?
Oh.
Optimal means either maximum or min. What is best? What is described in the question? Either it could be maximum or min. If they are asking for maximum, you are expecting maximum profit. If they are asking for a minimum, they are asking for that minimum loss, right? But both of them is optimal, right? Yeah. I think it's clear.
Yes, sir.
Yeah. Right. So now this is another interesting problem, but mostly this particular problem I found in the quiz examination only. See, generally the matrix multiplication. So the basic condition for the matrix multiplication is very simple. So if and only you can do the multiplication of two matrices, the condition is, so first matrix columns must be equal to second matrix rows. Is it right? Then only we can do that matrix multiplication. I think it's clear, right? This condition must be satisfied. Then only we can proceed for that matrix multiplication, right? Is it right?
Yes,
Yes,
sir.
sir.
For example, if you take that first matrix dimension is 2 cross 3, second matrix dimension 3 cross 4, it works because this matrix columns is this matrix rows is this, these two are equal, we can do it. That's a basic principle of matrix multiplication. I think that is pretty sure. Now the situation is, there is a matrix multiplication function. That function always takes two parameters. Maybe your function is that multiply. It always takes two matrices only. Maybe the first matrix is that M0, second matrix is M1. It cannot take more than two matrices to multiply them, because whatever code you have implemented is suitable for two matrices. So more than two is not possible. Now the situation is, whenever you want to multiply that two or more matrices, what are the different ways of multiply them? So for example, so let's take that maybe you can consider. So I don't want to discuss this. Yeah, maybe I'll open my another rough work so that to make it easy. See here, there are four matrices are given. Let us consider. So M0, M1, M2, M3. So M0 size is that 2 cross 3, M1 size is that 3 cross 2. So M3 size is that 2 cross 5, M3 size is that 5 cross 4. I think they are compatible to multiply, right? Because it's matching this 3 and 3, 2 and 2, 5 and 5, right? Right?
Yes, sir.
So what are the different ways to these four matrices? What are the different ways to multiply is? So if you could do that, maybe the matrix function, whatever you are using, two matrices, it's taking parameter. So you can do that. First matrix multiplication is M1, M2 result that we are multiplying with M2, M3, right? This is one way, right? Right? This
Yes,
is
sir.
one way. First time you are calling the function with M0, M1, then we are calling the same function with M2, M2. These two results again you are multiplying here, right? Similar way, you go with other combination also, M0, M1, M2, M3. First we multiply these two. The result we are multiplying with M2, then the result we are multiplying this one. So that this is one and this is second way. And third way you might have, like M0, M1, M2, M3. Maybe you can consider the third way. We multiply these two, then the result we are multiplying these with M1, then the result we are multiplying with M0. This is another way of multiplication. Still we have a chance of it. Maybe you can consider more. So let's consider. So some more thing you consider it. I can do that because the proper columns must be equal to the rows. That philosophy you must follow, right? Then only it's possible. So if you could go for still further. So M1, M2, M3. First you multiply these two, right? Correct? Hello? First
Yes,
you
sir.
multiply these two, then we multiply these two, then we multiply this one, right? This is fourth way. I think still you have another way also, like M0, M1, M2, M3. First you multiply these two, then we multiply these two, then finally we multiply with M3. So totally 4 matrices have 5 ways of multiplication, right? Is it right?
Yes, sir.
So generally there might be a quiz question. They might ask you that you have given that 4 matrices. How many different ways of multiplying these 4 matrices? You need to identify the simple, say they don't ask you more than 4. Definitely maximum 4 only. Like 3 they will ask it, 4 they'll ask it. Generally, I found the previous question. This is what they do. Now that is what exactly how this matrix multiplication with a function which takes the two matrices as a parameter. Now the situation is, out of all these are like 5 multiplications, which of them is optimized multiplication? Like number of multiplications is there, no? That is different from one multiplication set to other. So again, maybe I am going with my, still I did not enter into my this particular summary because I want to make you to understand what really happening. So let's take an example. Let's take an example. Because a number of multiplications we are finding. The number of multiplications here is different. So this might be number of multiplications are different. So in this pattern, the number of multiplications are different. In this pattern, the number of multiplications are different. Because you can say that there is example. See, look at here. There is a matrix I'm taking 2 cross 3, which the example elements are something like 1, 2, 3. And 4, 5, 6. So which is 2 rows and 3 columns. There is another matrix I'm taking, maybe it could be that M0. So another matrix I'm taking is M1, which is that 3 cross 2 matrix, where it might have that 7, 8, 9, 10, 11 and 12. Of course, my particular matrix bracket is not closed properly. Yeah. So I think these two are compatible to multiply, right? These two are compatible to multiply or not? Correct. So let's do a simple kind of what is happening inside, because we are interested to see that. So the multiplication approach, it follows like this. So 1 into 7 plus 2 into 9 plus 3 into 11. Similar way, 4 into 7 plus 5 into 9 plus 6 into 11. Right? Right? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Because this particular columns is multiplied with this particular rows. Similar lines if we go, so 1 into 8 plus 2 into 10 plus 3 into 12. Similar way, 4 into 8 plus 5 into 5 into 10, and then 6 into 12. So if you could, maybe calculation is okay, I'm not interested to do the calculation. Now, total number of multiplications is, I think 1, 2, 3, it is totally 12. Is it right? Is it right?
Yes, sir.
Total multiplications are 12, no? Is it right or wrong?
Yes,
Yes,
sir.
sir.
So whenever compatible matrices like M0 and M1, total multiplications you want to find out means very simple. 2 into 3, 3 into 2 matrices if you want to multiply, the number of multiplications are simply 2 into 3 into 2. Is it right? Is it right?
Yes, sir.
Because this 3 and this 3 is common, because in meanwhile we are doing addition, so that one of the 3 will go off, so that it's equal to the 12. So this is number of multiplications. So if M0 M1 is multiplied, we are getting 12 multiplications. If M1 and M2 is multiplied, then we multiply with M0. What is happening? So out of that, we want to identify the minimum number of multiplications. Out of that minimum number of multiplications, we want to find out it. Now let us consider, so maybe if you understand this concept, so little bit expansion I'm going. So I think this is expanded format. Maybe I've taken my own example. Let's take M0 is 2 cross 3 matrix, M1 is 3 cross 2, M2 is 2 cross 5. I think to multiply these 3 matrices, what are the different ways to multiply? How many different ways are there? How many different ways are there? How many different ways are there? To
2.
multiply three matrices. Yeah, first way is maybe M0, M1, then multiply with M2. Is it right?
Yes,
Is it
sir.
right? So another way is that M0, M1, M2 is that. First we multiply these two, then we multiply this one. Is it right?
Yes,
Yes,
Is
sir.
it
sir.
right? So in this way, if you want, the number of multiplications like we tested. So M0, M1, then M3 if you are doing, so it's definitely 2 into 3 into 2 first. Is it right? Is it right? Hello?
Yes, sir.
Yes, sir.
So it's going to be that 12 multiplications. Hope you got it, right? Hello?
Yes, sir.
Now, M0 and M1 if you multiply, what is my resultant matrix?
2 cross 2.
Correct. 2 cross 2. So this resultant matrix is going to be the 2 cross 2 and this M2 is available with 2 cross 5. Sorry, by this time. So yeah, after this particular one is done. So 2 cross 2 we got it. This is already existing is 2 cross 5. If you multiply this, what you are getting is 2 into 2 into 5. Is it right?
Yes, sir. 20.
20. So in this way, if you go, total 32 multiplications are required. Because this 20 and this 12, you do the addition, total 32 multiplications. Is it right? Hello?
Yes, sir.
Now, let's move in this way. In this way, if you go, these two if you do it first, because we are trying to do these two, 3 into 2 into 5. First, these two are done, 3 into 2 into 5. Is it right? Because 2
Yes.
and 2 is there. So 3
30.
into 2 into 10 is going to be 30, right?
Yes, sir.
Yes.
So whatever the resultant matrix, what is the resultant matrix for this 2 multiply?
3 cross 5.
3 by
3
5.
cross 1. Yeah, this is 3 by 5. This is already 2 cross 3. So 2 into 3 into 5. So that 2 into 3 into 5. So this number of multiplications 6 and 30. So total is 60 multiplications. Is it right?
Yes.
Yes, sir.
So out of these two, this is the best approach. That one we want to figure out using the DP approach. So that is what the idea of this, the last problem of this matrix multiplication. Yes. See here, the bracketing doesn't change the answer, whatever, multiplying sequence, either M0, M1 you are multiplying or M1, M2 you are multiplying, but it will affect that time complexity, the number of computation of multiplication you are doing. So based on it, the complexity can be reduced. Now, this DP's matrix is somewhat typical. Of course, maybe if you can again walk through this one, you can easily recollect it. So this blue color, simply it is not used and not required. Not required. Just we have a matrix, but we don't use the bottom values of the diagonal. This orange color one only we are computing. We try to ignore that bottom values. There is no use. We try to use the orange color part of this particular matrix only. Forget about this particular implementation because always implementation is very easy based on the inductive structure. Now, this part is important. Yeah. See, I'm taking this example. How these values of 120, 360, 720, 1680 is generated. Let's walk through that. So if you could see that there are 1, 2, 3, 4, 5. Maybe they consider it M0 matrix dimension is M1 matrix, M2 matrix, M3 matrix, M4. So let you consider in this way. This is M0, M1, M2, M3, M4 because 4 matrices. So similar lines you go at M0, M1, M2, M3, M4. Now, the thing is, this particular diagonal value, whatever, this diagonal value is used as base case. Why it is base case is, if you could check it, M0, M0, if only one matrix is given, there is no chance of multiplication, so that 0. M1 alone is 0, M2 alone is 0, M3 alone is 0, M4 alone is 0, so that we are using this diagonal values all 0, and this part is not necessary. We don't use this part. We don't worry about this part. We always go to the top of that diagonal values only. Now we are working about this 120. How did you get this 120? Can anybody say that? Because whenever this 120 to be computed, this combination of M0, M1 multiplications you need to find out. Is it right? Is it right? Hello?
Yes.
So whenever M0, M1 multiplications you want to trace out it, possibly M0, M1 multiplications based on the dimension 4 into 10, 10 into 3, it is simply 4 into 10 into 3. It is equal to 120. So this 120 we got in this way. Is it clear? Is it clear?
Yes.
Similar way, M1 when you are considering this particular M1 and M2. So this M1 and so whenever M1 is considered, so M1 alone is okay, but whenever you consider about M2, M1 and M2 if you combine, so multiply, sorry. So then M1 and M2, if you multiply that, so if you say that 10 into 3, 3 into 12, so that it's going to be that 10 into 3 into 12. It's ultimately going to be 360. So that way we got this 360, 720, 1680. I think up to that it's clear, right?
Yes, sir.
Up to the two matrices is not a problem. Whenever we are expanding to M0, M1, M2, so that your expansion level goes to this part, then there is an interesting thing happens. So you need to figure out it. So what we need to figure out it is, so the minimum one we are finding out it. So what minimum? For example, we are trying to move some more extension, like I'm just moving, maybe this filling is okay. Now we are working about what about this 264? We are trying to trace out this. So to move to this trace out of this, so we have M0, M1, M2. So what way it is happening? So to do this, there are two different ways of doing, because three matrices means two different ways. So we have that M0, M1, and then multiply with M2. This is one way. And another way is available, that is M1 and M2 first, then the result we are doing with M0. So now let's figure out this one. If you figure out this M0 and M1, already 120 is there, the previous value I can use it, right? Can I figure out this 120, is it? No? Can I use this one?
Yes.
So I can use this 120 as it is, but whenever you are trying to get this multiplication of this M2, the resultant matrix of these two, the resultant matrix of M0 and M1, so if you consider 4 into 10 into 3, what matrix you are getting this? So 4 cross 3, right?
Yes, sir.
4 cross 3 and then 3 into 12. So that 4 into 3 into 12 you are getting, right? Is it right? Hello? This part I am talking. Hello?
Yes, sir. Yes.
So that 4 into 3 into 12, it's going to be that 4. Yeah, it's 144, right?
Yes, sir.
So this total, this total is going to be that 264. Let's see that what is happening this part also, because I should know that what is happening in this part. In this part is M1 and M2 already 360 is there. Of course, this 360 itself is crossing the limit of 264. Even before doing multiplication, even if you add it, whatever the result we got at M1, M2, and then we multiply with M0, it is more than 264. The minimum of this part and this part we are extracting, that is called 264. Similar way, you filled these parts of it. If you could see that index to structure, maybe it's a typical index to structure, but very easy to know that. So the index to structure of the base cases, see here, all the diagonal values only. Forget about these things. This is not required, the bottom part. So whenever I and j is equal means the diagonal part we are filling, base cases across diagonal. So other than the diagonal, we are going to the top. What I do is, we try to do that, the minimum of that, the previous two things, like current k and the k plus 1, like that's what, sorry, the previous dimension, and as well as new dimension we are calculating, whatever the new dimension you are computing. So all these things we'll put it in list. Actually, in the coding implementation, I'll show you that. All these things we'll put it in a list. In this list, we are trying to find out the minimum, because this particular k, it is greater than this I value and as well as less than this j value. So there is a nested loop is running. In this nested loop, we try to calculate the each dimension. Out of this, all these is we are putting or appending into the list, and we try to find out the minimum one. So you can see this one here. Yeah. See, there is a KL is appended. So using this index to structure. Using this index to structure, the KL is appended. After appending job is done, we try to find out the minimum one. That minimum one we are updating in this particular one. See, this 264 is updated, 1320 is updated, 1140 is updated. That is done. Out of this list so far we got it. In that, what is the minimum? We got a list of 264 and 360 above. Out of these two, the minimum where we are picking, we are updating this minimum one. So similar lines we do it. That is what implementation is done. So finally, what you written is the last top right corner one we are finding. Top right corner one means it is n minus 1, 0th row. So that is what this final value we are getting. So to multiply the 5 matrices, the optimized approach requires that 1344 multiplications whenever the dimensions are taken in this way. The dimensions are taken this way. But if you could follow that, still the notes, you can identify this part also. So what is this part? It is very interesting. The kth position it is showing. The parenthesis position. See, 3 they are giving, 1 they are giving. This parenthesis position they are taking. So what is this k is that the parenthesis order they are providing. So if you could look at which k is the minimum one, if you could look at this 4 matrices, M0, M1, M2, M3 and M4, because totally 5 matrices, sorry. So in this particular one, which combination is worked for me? Like the parenthesis only here makes matter. The number of multiplications is reducing based on the parenthesis where do you put it. Now, if you could see that, so we are trapping from top to bottom, like like this one, and we are going to the down. The first parenthesis you need to put it at kth matrix. Kth matrix means here this is a k value. This is a k value. So first parenthesis you need to put it here. So because this is the k. Then, so where should I put that second parenthesis? The second parenthesis you need to put it at this place, because this is M0, M1, M2, M3, M4, M0, M1, M2, M3, M4. So if you put it this particular parenthesis at this place, so third one means we need to put it at the end of this particular one. So when you are putting at this place, definitely these two are multiplied. And the result of these two and these two are multiplied. So after that, so whatever the result we got it, maybe, these two are multiplied. And yeah, there might be one more you need to figure out. There it is, wait. So first one is that M0, M1. Next we found it is M2, M3, M4 is there. We move to the next order so that, so M3 we are putting the next one. Yeah, it is okay. Then the, see. So which the 3 can parenthesis. So third one, this is the K value. K value is 3. This is the K value is 1. So, and the last one, where they are putting the final order is, okay, yeah. So the result of this one and this one is multiplied. Yeah, it is okay. Yeah, good. The last one is this part, because the result of these two, again, we are multiplying with M4. Yeah, got it. Yeah. So this way we have to figure out it. See, this particular kth one is representing, where do you place your first parenthesis? Where do you place your third parenthesis? If any second parenthesis is using, maybe, more number of, still the matrices are there, still we go to the bottom level, still we go for the kth parenthesis position. So this is what really, the dynamic programming. But this inductive structure is somewhat complex structure, but mostly we don't ask you that, giving a bigger kind of dimensions of matrix. We don't ask you this kind of a bigger value like 13, 44, something like that. Generally, what way we are asking is, actually, I've seen that earlier things. Generally, they try to ask you this way, like they are taking a simple M0, M1, and then M2. What is the optimized way? Like 3 matrices only they are giving. How many multiplications in this order you need to find out it? That is 32. How many order of it? What is the optimized way? Either 60 is the optimized way or 32 is the optimized way. Just you need to figure out of these two one, which is the optimal value. So that's it. Mostly the complexity quiz question we ask it. And in DP programming, whenever the matrix multiplication in the OPP examination, we even passed pattern of examination, we never found it. There is a question on the matrix optimized multiplication. So that is what really we want to share it. So I think everything is clear. Any clarification?
Sir, can you once go to that parenthesis part?
Correct. Parenthesis part. Yeah, this is the part of it. Yeah. So first parenthesis is this part. Yeah, first parenthesis is that, yeah, top to bottom we are going. First parenthesis, we need to put it at the matrix number of 1. K is 1. This is the K. We need to trace out that current K value. This current K value is there, that it will decide. Yeah, current K value, it will decide. Whatever the current K value is there, that will decide current K value. So they will pick out that current K value. Based on it, we'll put that particular parenthesis. This one.
So then what does 720 by 2 mean? Like we have to put parenthesis.
Still we are going to that further. Like, maybe instead of 5 matrices, still there might be 6 matrices are there. Then you require another submatrix multiplication, something. By doing this K1, by doing this K3, we got these two, right? We got these two. So the result of this M0, M1 can be multiplied with M2 and M3, right?
Yes, sir.
But if you do M2 and M3 and M4, there might be a situation. So you cannot do the resultant matrix of M2 dimension with M4. Maybe unmatched kind of thing you are getting. I don't know what kind of value is that. Maybe you are putting this one here. Maybe you can know that. See here, M0, M1. This is first part. M2 and M3, clear? So this
Yes.
is K is 1, this K is 2, sorry, K is 3, because this is 1. So whenever next multiplication, if it is optimized to this particular M4, maybe the next level, it might show you the next level. Instead of this particular the K3, maybe the next level, it might show you that K value is 4. So at that time, you supposed to put that another parenthesis here. Then you supposed to multiply this part. Whatever the result we got this, then we are multiplying this result of this R1 and this result, we are multiplying these two, right?
Yes, sir.
Maybe if optimized value are getting, so then you might have K value is 4 also. When the 4 value are going, next parenthesis we are putting it fourth one. Yeah.
So only we have to just walk down the last column.
Correct. This last corner is that optimized number of multiplications for 5 matrices with these these dimensions. Okay.
Yes, sir.
But we don't ask you this much of bigger one, but only we'll ask you that number of matrices are 4. How many unique ways to solve these matrices? That is one. And another one, what I said is this in the rough work, this one, like simple 3 matrices they're asking. What is the optimized matrix multiplication, number of multiplications? Either you need to compute 60 and 32, we need to figure out 32 is the minimum. Yeah. Yeah, somebody wants to ask something. Yeah, cool.
Sir.
Vishwa.
So, in this problem, like we are seeing that the best optimized way is to go from left to right. Like we are adding the first two and then, multiplying the first two and then multiplying the third one with the existing product.
Correct.
Then what is the use of other options, like multiplying two in between, like M2 and M3, and then M0, M1, and then multiplying those?
See, so whenever 2 is there, yeah. So whenever 2 matrices, simply we are getting this. Whenever 3 matrices is there, there might be this one is optimal solution or this might be optimal solution, right?
Yes.
Out of that minimum we are selecting, right?
Yes.
So whenever extension goes to this M0 to M3, there are 5 different ways are there, right?
Yeah.
So each way you need to find out it.
Okay, but with the examples given in the slides, it shows that
where is
the optimized, like in these slides, the examples given.
Where is the example? Okay, this one?
Yes.
This example.
With this example, it shows that the best way is to go from like multiply the first matrix and then multiply the third one with the existing one.
Where is that?
Like
it was given?
The matrix 410. Previous slide, last line.
This one?
Yes, this one. 410, 10, 3, 312.
This is okay? Yeah. We got it, no? Right? This
Yes.
one only I used it. This one. This is filled with this, right?
Yes, but in this example, it is implied that like we are multiplying the first two and then multiplying the third one with the first two.
No. We see the product, these two we are there. Then we are doing is whenever this extension is done, out of these, see whether this is the optimal one or these two are multiplied, this is the optimal one. Out of this 264, see this 264 we got it, this 360 we got it. We are updating 264 only. 264 one means these two are multiplied first, then we are adding this, right?
Yes.
But I need to figure out the calculation, count the dimensions, then only I'll get it. No, without knowing, how can I say that, right?
No.
I have to do the dimensions finding, no, right?
Okay, like we are also finding the dimensions.
See, we don't multiply, but we find the dimensions and compare, right? See, here the dimensions and we compare. Like these dimensions If you do that, how many multiplications?
Okay.
It is 360.
In question, the dimensions might be shuffled up,
Correct.
like 410, and after which it can be 312.
Correct. Okay. Okay. Yeah. Yeah, it is, I think, pretty much that. But DB have the two ways of it. As I suggested, you might be very careful about the conceptually in the quiz examination, as well as the DP in that implementation. Still, we have a Friday session where it could be that live coding one, where you will find that more DB problems, but make sure that you must attend for that. So practically you will understand for upcoming OPP examination. That would be very helpful session on upcoming Friday. So hope you got it. So thank you very much. Have a nice day. I think we can close the session.
Thank you, sir.
Okay. Thank you, sir.
Thank you.
Thank you, sir.